Okay, now we're going to discuss another type of simple harmonic motion, the motion of a pendulum. Um, so let's bring up the PowerPoint, and there it is. Let's move this over. And another system which exhibits periodic motion is a simple pendulum, which consists of a small bob of mass m suspended by a light string of length L, fixed at its upper end, as in the figure. By a light string, we mean that the string's mass is assumed to be very small compared with the mass of the bob, and so we can ignore it. When the bob is released, it swings back and forth, tracing the same path. But is this simple harmonic motion? We'll need to look at the restoring forces, in this case, the force of gravity that acts on the pendulum. There it is. Force of T is equal to minus G sine theta. The pendulum bob moves along a circular arc rather than back and forth in a straight line. When the oscillations are small, the motion of the bob is nearly straight, so we can apply Hooke's law. In the figure, S is the displacement of the bob from equilibrium along the arc. Hooke's law is F equals minus kx. So we are looking for a similar expression involving S, where F sub t is the force acting in a direction tangent to the circular arc. From the figure, the restoring force is shown here. F sub t equals mg sine S over L. Okay, since S equals L theta, the equation for Ft can be written as shown. This expression isn't of the form F equals minus Ks, so in general, the motion of a pendulum is not simple harmonic. But for small angles less than about 15 degrees, the angle theta measured in radians and the sine of the angle are approximately equal. You can prove this to yourself. Just do a spreadsheet and do the angle between, let's say, minus 30 and 30, and the angle and the sine of the angle. Take a look at this example for 10 degrees. There it is for 10 degrees. That means if we restrict the motion to small angles, our approximation that sine theta is about equal to theta is valid, and the restoring force can be written as shown here. Okay, F sub t is approximately minus mg theta. Substituting the expression of k for a pendulum, which is mg over L, we get this result. This equation follows the general form of Hooke's force law. So we are justified in saying that a pendulum undergoes simple harmonic motion only when it swings back and forth at small amplitudes, or in this case, small values of theta, so that sine theta is approximately equal to theta. You remember that for the object spring system, the angular frequency is given by the equation shown here. Omega equals 2 pi f, it's equal to the square root of k over m. Substituting the expression for k for a pendulum, we obtain this relationship, omega equals mg over L divided by m. Well, you'll see that the m's cancel, and we get the square root of g over L, omega equals g over L. This angular frequency can be substituted into our equation for the displacement, which now mathematically describes the motion of a pendulum. A cosine omega t becomes x equals a cosine square root of g over L times t. This equation reveals the somewhat surprising result that the period of a simple pendulum doesn't depend on the mass, but only on the pendulum length and on the free fall acceleration. Also, the amplitude of the motion isn't a factor as long as it's relatively small. Omega equals 2 pi f. The period is equal to 2 pi lg. There is no mass in there. People think that, well, the heavier the mass, that that'll affect the oscillation. It doesn't really. It just depends on the length and the gravitational acceleration. So a similar pendulum swinging on the moon would have a different period than the same length swinging on the Earth. Whoa, went too far. And we are, okay, we're still going. Okay. If you look at this figure, the figure shows the analogy between this motion of a simple pendulum and an object spring system. In a little bit, I'm going to show you a Walter Fent demonstration using a pendulum. Galileo first noted that the period of a pendulum was independent of its amplitude. He supposedly observed this while attending church services at the cathedral in Pisa. The pendulum he studied was a swinging chandelier that was set in motion when someone bumped it while lighting candles. Galileo was able to measure its period by timing the swings with his pulse. Because of the dependence of the period of the pendulum on the free fall acceleration, we can use the pendulum as a timekeeper, like a grandfather clock. Of course, these clocks are used at different locations on the Earth, so there will be some variation of the free fall acceleration. These types of clocks generally have some movable mass so that the effective length can be adjusted. Geologists often make use of the simple pendulum when prospecting for oil or minerals. Deposits beneath the Earth's surface can produce irregularities in the free fall acceleration over the region being studied. A specially designed pendulum of known length is used to measure the period, which in turn is used to calculate G. Although such a measurement in itself is inconclusive, it's an important tool for geological surveys. Okay, a pendulum, however, can be made from an object of any shape, not just a mass on a string. The general case is called the physical pendulum. In the figure, the rigid object is pivoted at point 0, which is a distance L from the object's center of mass. The center of mass oscillates along the circular arc, just like the simple pendulum. The period of a physical pendulum is given by the expression shown here, where L is the object's moment of inertia and M is the object's mass. As a check, let's take a look at the special case of simple pendulum with an arm length L and a negligible mass. The moment of inertia is I equals ml squared. Substituting into our equation for the period, we get the expected results. There we go. And that's it for this section. I'm going to show you the Walter Fent oscillation next.